From ContainerDays Hamburg, this video is proudly presented by DAX IT.
Thank you for being here, and thanks for joining our talk. We'd like to share with you how we can leverage intent-driven approach to simplify network automation. My name is Alexander North. I'm a DevOps engineer at Swisscom. Swisscom is Switzerland's largest telecommunications provider. I'm part of a team managing automation, and specifically I'm working on managing the automation of configuration of the 5G mobile core.
My name is Markus Vahlenkamp. I'm a technology and architecture consultant at Nokia. I'm working on network management in general and a specific focus on cloud-native network management.
So, I said I'm working with the 5G mobile core. What exactly is this? Well, it's a network architecture which provides essential functionality for mobile communication as well as protocols. Here is a small picture diagram of one. If we look at each of these blue objects, these are a cloud-native network function. That is, for example, a router or authentication service. It's how we can monitor things like your bill and your data usage. These are deployed using a Helm chart, and configuration is done both through Helm values as well as other configuration protocols. One of these is NETCONF, which we will come back to a bit later on. In terms of scale, each of our development environments contains around 2,000 pods. And within these 2,000 pods, we're talking about around 5,000 interdependent configuration parameters. Now, if you look at a general cloud-native application and how you would configure it, you would have some deployment. You would mount a config map, a secret potentially, to define how it should behave. You'd place a service in front of it, and this is how your consumer will interact with this application. Unfortunately, not all applications are completely cloud-native, and they require some extra work first. Take, for example, a database. You have the same setup, you have deployment, you have your config map, your secret, potentially to define some behavior. But before it's ready to use in an application, you need to first create a database, create some tables. A cloud-native function is similar to this. Instead of a SQL query, we have NETCONF, which is a protocol for configuring this device. This is an ongoing process. It's not just an initialization time. So we really need something that can support this. Up until now, we've had an imperative approach. There's a pipeline that takes a configuration template, renders it, and pushes it straight to the CNF. It's a one-shot approach. We trigger it, we hope it works, that's it. If we have errors in the configuration, we can only detect this at the time that the configuration is pushed to the device, not prior to it. We have an issue with monitoring. We don't know if there's a parameter on the device that's changed between the time that the configuration was pushed and the usage of this device in the network. And because we have such large configs, if we want to split this up to try and maintain traceability of changes, we lose the ability to view the overall picture. On the other hand, if we have one large configuration, we lose all information about where this configuration comes from. We have a monolith. So can we do better? Well, there's a tool that we all know quite well that does things in a declarative way to reach some goal, Kubernetes. Are we able to borrow this approach and apply it to configuration management? What are the building blocks? We have an API extension. Here, we define a structure of a new Kubernetes resource. We then have some kind of CR that defines the state that we want the system to be in. And we have something that moves from the current state to the state defined in the CR, the state that we want. It does this through a control loop. And this control loop registers with the Kube API and asks to watch for specific resources. It then will perform actions to move the state of the system from the current state into the desired state. And finally, it will update the resources to reflect the state that we're currently in. There are some built-in operators that you may have come across, deployment, job, persistent volume operators, for example, as well as some third-party tools that are quite popular, for example, Prometheus operator, external secrets operator, and cert manager. So we have some way of addressing this problem, but what is our problem domain? Well, here we're talking about networking configuration protocols. There are three widely used protocols, NetConf, gNMI, and RESTconf. They all have various approaches to transport and encoding. For example, NETCONF uses SSH, gNMI uses gRPC for transport, and NETCONF uses XML, and gNMI uses Proto or JSON to pass the configuration around. However, they all have a common base. This is the Yang schema. This allows for conversions between encodings as well as validation. So we have a way to streamline or unify this. The Yang schema itself is a modeling language of a configuration tree. It can become very complex, but I want to show a quick, simple example here. On the left-hand side, we have a schema, and on the right-hand side, we have an XML representation of a configuration that matches this schema. We start here by having a list of device. We have some attributes on this. So for example, we define a key to be able to look up items in this list, and we have a constraint that we have at least one element. On the right-hand side, we see we have 2 blocks with device, which means we have 2 device items there. We can define then leaves, which are config values. Here we define a name, which is exactly what this key defines on the list, and we have a type string here, quite a simple case. Then we could have, for example, a role. And here we have an enumeration, which means that the value has to be one of these predefined values in the enumeration. We also see that it's got mandatory true, which means it must appear inside the configuration that's passed. In this case, for the final leaf load, we have a management IP. And this is importing a type from an external module, in this case, iNet. Here, it's defining an IPv4 address, and we have a case where we have a must validation statement. These are arbitrary validation rules defined in XPath expressions. And in this case, we're saying that the value that's set here must start with 10 dot. On the right-hand side, we can see that these have been reflected in the XML config, and according to the schema, this is valid. So now we've defined our framework, we have a problem domain, and I'll hand over to Markus to explain how we went around solving.
Thanks, Alex. So Alex has actually introduced to us the building blocks that we need to lift our network configuration management into a true cloud-native network management system. So we need the CRDs that define our domain-specific information. We need the reconcilers to work on these. We need the schema, and we need to implement the protocols to push this configuration. So this is this is something that we at Nokia took up as a challenge to implement all of that in a project, and that's how SDC, or Schema Driven Configuration, came to life. We've open sourced SDC last year, and it's available on GitHub. We actually also pushing on the community for SDC. So we have a Discord channel that we offer support, be there for discussions, and have regular meetups on Mondays. And we're aiming to become a CNCF project. So let's take a look at the components that SDC is actually built of. First, we have the config server, which is an aggregated API server. It contains the domain-specific resources, as well as the reconcilers for those, and it translates then the Kubernetes API resources into our SDC internal model. We have the data server. The data server builds an in-memory configuration tree. This configuration tree is fed on one side from config server with the configuration intents that you push into the Kubernetes API, and from the other side, it gets hold of the network functions configuration via the named protocols. It is building a tree with all these information included, and trying to figure out the expected state and the difference between running and the expected state. The difference is then later on pushed to the network function. All of this is backed by the schema, as mentioned. The schema server is a service that can be queried with a path to acquire the actual schema element. These elements then contain of the type of information and all the validation rules and the constraints that each and every element has. So what are the main custom resources that we provide in SDC? First of all, that is targets. Targets is the representation of the network function from SDC lifted up into Kubernetes. So in Kubernetes, you will see that device is reachable, we can configure it, and so on. The next two are configs, our config intents, which might be snippets or even full device configurations, and config sets, which are blueprints of configurations. These blueprints are configurations that might apply to multiple targets, and they'll be matched onto these targets via label selectors. We also provide the running configuration from the device through the Kubernetes API. That's done in the running configs resource. So all your configuration that's running in the network will be available in your Kubernetes API. Deviations. So we do not force you to push or maintain the entire configuration via SDC. You can still go onto a box and do manual changes, and we accept that. But that results in deviations from our actual intended state. And what we did with deviations is to report these deviations from the expected state back into the API. And we have config blame. So let's consider we have 200 configuration intents because you chopped your whole configuration up into very many pieces for each and every interface, for each and every service, and so on and so forth. So it can become quite a large number of config intents. And config blame will give you the opportunity to figure out from the running configuration of the device which intent actually promoted this value to our configuration. And we'll see that in a bit. So let's start with the configurations. Here we see a running configuration. So we pretend that we've configured our device with configuration intent already, and this is the state that is reflected back into the Kubernetes API right now. So we can now go and add an additional interface in this case, which is point 1, and also an additional services number 2. And beyond that, what we'll be doing is changing an existing value. So we have in the running configuration an IP address already set for Ethernet 0, and we'll be overriding that with this new intent. And that will, in the end, after SDC picked it up, it will be reflected again in our running configuration, now having the new IP address, plus the additional interface and the service. So now you might have the question like, why did it update the IP address? There was an intent, there is another intent. what's happening. So we foresaw that configuration intents might overlap. And that's why we came up with the concept of the priorities that you see down there on the bottom. So a higher priority configuration intent will win over a lower one. So in this case, the priority of the second configuration is higher than the initial one. And that's why this value is taken into the running configuration. The good thing here is, as soon as I delete the second configuration, my initial configuration is still there because it's stored as an intent, and that value will be restored. Then there is some other flag, which is called revertive. The revertive flag is a flag that tells SDC if you see any changes that someone might have done manually to the device, and it's changing a value that is defined in this intent, please go and revert it straight away. So that's strict mode of operation. But you can also say revertive false, and then what we do is we do not revert that value straight away, but report it as a deviation. And that deviation you can then take a look at. So here we have the deviation CR, and you see that for the path network service A bandwidth, we have a deviation. And that deviation is associated also to the initial configuration intent, which is, in this case, even called initial configuration. And we see that the expected value due to the intent is 5,000, but someone went to the device and changed it to 100. So what can you do now? You can go and delete this deviation. That will do the revert for you. So by just changing this resource, you can manually do the revert. You could also be like, okay, this is a temporary fix for something. I want to keep it, but I want to keep track of it. So you leave it as this deviation, and it's perfectly fine. Or you just go and realize, like, this is really the value you want, and you go and change the initial intent to this specific value, and then also the deviation will go away. That's just one reason for deviation. That's the not applied deviation reason. And then the others would be overruled. That is, there is another intent for this specific value that is of higher priority. So that's why this is not become inactive. And then we also have unhandled. Unhandled means that's brownfield config, so there is config on the device where we do not have any intent for, and therefore we reflect it into the API and tell you there is configuration on the device. There's no intent for it, but we keep it, we work with it, and we'll be fine. And now back to the to the initial scenario where I said we have 200 whatever configuration intents that we've applied to a single target, and now we need to figure out, like, what's the source of a specific value in our configuration. So what we did is we built a kubectl plugin, SDCIO, and that has a blame command. It goes off to the Kubernetes API, queries the blame resource, which is in the API represented as a JSON struct. So not really helpful, but with this kubectl plugin, what we do is we take that JSON information and we render it nicely for you. So in here you see that the admin up true on the Ethernet 0, for instance, is coming from the initial configuration. The next item, the IP address, is coming from our overlapping config, and so on. And this is really the actual running configuration on the device. What we also add is the default values that are coming from the schema. And then down at the bottom, you see the brownfield configuration. That's configuration no intent specifies, but it's sitting there on the device. And as an extra, under point 2, we also put deviations in here, right? So with this star, you see, okay, this is meant to be the bandwidth attribute is meant to be 5,000, but it's actually 100. And now you can take action. And with this, I'd like to hand back over to Alex, who's showing us a demo.
Thank you, Markus. So, sorry. Now, here I have a setup, a local setup of SDC, along with a demo dummy device. At the top, we're showing 2 resources in the Kubernetes cluster. One is these configuration snippets, these configuration resources, and the other one are the deviation resources. In the middle, you can see the cluster pods running. So we can see that we have this demo device, this test device. We have an SSH pod, so we can access the CLI interface of this device. And we have config server, which is our SDC deployment. At the bottom, we have the SSH interface, the CLI of the device. So what I'd like to show now is a little bit what you've seen in the slides that Markus presented. And to do that, we can start with showing what the running config looks like. So if we go to watch the running, we can see we have this initial configuration that was shown on the slides. Very plain, we have our 2 interfaces, ETH0 and the loopback, as well as our single service. So now, let's say we want to apply some new configurations. Here, we're going to apply the new interface and an overlapping configuration. These are the 2 additional configuration snippets that were shown before. If we then look, this is the running configuration that we see now. We can see that the values that were taken from the overlapping config as well as the new interface are there. We have this overlapped IP address and our Ethernet 1 IP set there. This is nice. We can see in Kubernetes the actual running configuration on the device. However, it's not so easy for us to read, as Markus said. So what we can do is have our blame view as well. Here we can see each of the resource or each of the configuration parameters along with where they came from. So on the left-hand side, you can see we have initial config, overlap config, as well as the new interface listed here. And this is really good to, as Markus said, see when you have a lot of configuration intents where the value actually is sourced from. Now, what happens if we go and modify a value on the device? Well, to do this, I'm going to go into config mode and set the bandwidth of service A to be a different value. So to do this, we have to follow the config tree to network service A, bandwidth. And let's say we're setting it to 100. So we're doing the exact manual step that we were showing previously in the slides. I commit this change, which means it will then update the value on the device's interface itself. Now, I'm going to, in this window, show again the deviations and watch the deviations. You'll see that we already have a couple of deviations there. These are from the fact that we have already overlapping intents. So the reasons that Markus showed before, we had this overlap reason, and that's because we have some intersecting configurations. If I now go to watch deviations, we will see that now we actually have our overridden, or we have our overridden rules deviations as well as our not applied, or in the non-revertive mode, something that was manually changed on the device. Now, let's say a network engineer was playing around on the device, did some testing, decided, no, this value doesn't make sense anymore. I don't want that there anymore. How can we get back to the state we were at before? Well, we're in non-reverted mode, so it has to be a bit manual. But to do this, we can just enter the, we can do a kubectl edit on the deviation resource and go down to our deviation that is not applied. If we remove these lines and then save and quit, we'll see that the deviation, if I go to watch deviations again, has disappeared. You can also see at the bottom maybe a small message saying that there was a commit performed. This means that SDC pushed something to the device now. I can also go and show that this is actually correct on the device by following the running configuration, for doing the path again. So we go back to our service A, and our bandwidth. And here we can see that the value has been reset back to 5,000, the one that's in our intent, our original intent. Good. So now I've shown what happens when we apply configurations, but where do we get these configurations from? Well, yesterday, my colleagues Alessio and Adrian, they presented a little bit about how we're building up many layers of abstraction to configure our interfaces or our network devices. So this slide might look a bit familiar, but I want to show how we're tying SDC into Swisscom's layered automation approach. So we're starting with a high-level intent, and we're stepping through multiple stages of abstraction, each one building on the previous level. We can do this many times, multiple times, as many times as you want, getting to an nth level abstraction, which can have be as abstract as you need. However, at some point, we need to turn it into something that the device understands. And so we need something here that will take this highest level abstraction and build it into something that it can be understood by the device. So this is the vendor or release-specific final stage. And this is something then that we can push to the device with SDC. So this is where SDC comes in our layered approach. And we get quite a few benefits with this. We can reduce our toil. So we're simplifying the configuration management. We are dealing only on high-level essentials. We're not caring about low-level details, IP addresses, and VLANs, and so on. We only care really about, initially, a high-level intent, and that's what will then filter down. Reliability. So Kubernetes operators don't sleep. They're constantly reconciling. If anything changes in the state, it will then make sure that the intended state is restored in the cluster. Network engineers only need to specify an intent. We don't need specifics. This increases efficiency as well as scalability. We no longer have such complex configurations that we need to manage and deal with. We can really split it down into small components and deal only with these. With that, thank you for your attention. On this, behind this QR code is some information about SDC, the documentation. And with that, I would open the round for questions. Thank you.
Is your approach compatible with declarative GitOps practices? I'm skeptical. Oh, I will highlight this one. I'm skeptical because deleting a deviation has side effects. It's running config.
So the deviation resource is a resource that's created by SDC. It's not something that's checked into Git. This is sort of in some of the other Swisscom talks, there was this conversation about split source of truth, where you have an intent stored in Git and then some Kubernetes managed resources. The deviation resource is one of these Kubernetes managed resources. So it's representing a state of the current system, but it's not something you would check into Git. It's just an interface for you to see what's going on behind the scenes.
Thank you. It appears that an intent can contain several sets of information that conflict, which leads to deviations. How do you unify this with single source of truth with GitOps? You can skip the questions as well if you want to.
So, I mean, this is a bit similar
yeah, it's very similar
to the last question. We can have overlapping configuration resources.
Yeah.
The idea here is that you don't need to necessarily in the lab environment work directly with the CNF or the network function. You could create a temporary resource that overlaps. The goal in the end would not be have overlapping resources or overlapping configuration parameters in a production environment, but it's useful in a way to see in the lab stage, do quick iterations and see what works best for the next step.
I mean, if you have a single source of truth and you follow this processing, there should only be a single config that pops out of it, and then, yeah.
Did you create your own CLI to make user experience with your CRDs better, or are you working with plain resources?
So yeah, for the blame command, for sure, you cannot really read the content of the tree. That's impossible in there. So we made it to have a better user experience interpreting this configuration tree. For the rest, we basically built up on plain kubectl.
Thank you for answering that question. Maybe you can choose the last one you want to answer on the stage, and all the other questions you can leave for the discussion later. Is there one you prefer?
Maybe the vendor-specific one. So the second one here, do you need vendor support to enable SDC?
Okay.
I think one of the key concepts of SDC is to be vendor agnostic. So we didn't want there to be a lock-in to have pre-approved support there. Yang is a RFC, so it's an open standard that has defined rules, and anything that is using Yang as a backing schema, then this could be used with SDC.
Thank you. Are you open for a discussion after the talk, maybe with others here, so they can come to you and ask the questions you have not answered so far? So feel free to come downstairs or join the session afterwards. Thank you very much. It's the end of the day at this stage. Thank you to you both. Applause.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.